Hey guys, welcome back to another video. This video is going to be the entire full in-depth course on the A2 physics gravitational fields topic. So I've compiled together all of the videos on our playlist that we have previously published into this one video. And I've also added one pretty small but big video at the very end, which is a new video that I've added. So hopefully this entire course will give you complete in-depth understanding so that you can score full marks on any sort of complicated, difficult question that comes your way, right? So hopefully this video is helpful and see you on the other side.
Now, right before you to get started, I want to put everything that we have to offer at Science Stadium in front of you guys. So we will be using the A2 Physics Black Book extensively through this course and all of the other courses that we'll be putting out there for physics, right? So you'll find this individual linked down below and will also be included in our A2 Physics course pack, which includes a number of things which you can take a look at it, but I will run through them very quickly. It will include the A2 Physics Black Book, which you've seen over here. It will also have the A2 Physics hard question compilation, which means all of the hard questions from paper 4 included topic by topic over here. So if there are like 14 topics, you'll have a hard question compilation along with its own mark scheme answer. So along with that, this is mainly for all of those top 1% or 5% student who wants to make sure their approach is completely foolproof and they don't want to lose any sort of mark on the day of exam. So if you want to practice all of the hardest questions, this is perfect for you. Now we have also included and written the A2 Physics Paper 5 Black Book, and this includes an elaborate PDF individually for question 1 and question 2 taught in details. What we have done over here is something incredible. For both of the questions, you will find work examples for each and every topic possible. Just to give you a perspective, for example, question 1, there are probably around 6 to 8 set type of topics and question types that can come your way, and we have laid down type of question and the model answer. So we have shown the entire structure of how you should be answering and also given you examiners insight. What do examiners expect from you when you're writing your answer? What to omit and what to include? Along with that, we have recently also included the A2 Physics Paper 4 Black Book. What is this? It includes all of the mark scheme definition. A lot of our students and a lot of the people who have purchased the course pack have that is known that they need or want the mark scheme definition such that they can make sure all of these basic questions, basic marks can be attained, right? And often you end up losing 1 or 2 marks based on not writing the exact keywords that is there in the mark scheme. So for that, we've included around 75 definitions in the course pack in the A2 Physics paper for Black Book. Not just that, we have also included around 24 most repeated questions, calculation-based questions that have come in the last decade of papers, and we've included that over here. Once you do purchase the A2 Physics course pack, you no longer need to get anything else because we will keep updating this and you will have lifetime access to it. So any update that we do bring into the course pack, you'll get it lifetime for free. And ultimately, we have the A2 Physics Live batch. It is not always available, but whenever we do launch it, it will be available to you in the course, in the video description or in the comment section. The thing is, sometimes we run out of the seats and the intakes are not always throughout the year. It is in specific times of the year. So if you don't see it right now, don't worry. It will soon be available for the next cohort or the next batch. And it will, of course, include all of the resources in the course pack plus more. And it will have weekly live classes with me or other teachers on Science Stadium. And you'll be covered with all of the content of paper 4 and paper 5. And you will also be having 1 or 2 mock exams with feedback based on your progress through the batch. And all of them, we have tried to make sure the price is as suitable as possible and we can welcome all of you guys. Lastly, thank you everyone for supporting Science Stadium, and I hope we can help you guys with all our free content out there. So see you on the other side.
Hey guys, welcome back to another video and another series. In this series, I'm going to cover the topic gravitational fields. And in this video, I'm going to talk about law of gravitation. So in general, we know that every object, be it you, be it a pen, has a weight. And it has that weight due to gravity acting on it. So let's say you and me on this planet Earth, we have a gravitational field acting on us, which is why we're being able to walk around, right? So that gravity, that amount of gravity turns out to be 9.81 in our case. That is 9.81 newtons of force per unit mass. So if you're 1 kg, the amount of force being exerted on you is 9.81 newtons. Now, why do we have this gravity, and how do we understand what amount of force is being exerted on us? Now, it is a given that gravity in case of Earth is 9.81, but how did we find this out, right? So to understand that, how this specific amount of force is being exerted on us, we're going to understand the law of gravitation. And we're going to see that for different objects with different mass, they're going to have different amounts of gravitational field, exerting different amounts of gravity on, let's say Mars is going to have a different gravity, and let's say Moon is going to have a different amount of gravity, because their field strength, that gravitational field strength, is going to vary. So to understand that, we're going to first understand what gravitational field is. So it is a region of space where a mass experiences a force due to the gravitational attraction of another mass. So let's say in our case, it's Earth, right? It is going to have its own gravitational field that is attracted towards itself. Now let's say there is another mass which has its own gravitational field. Let's say this pen. Now, due to its small mass, it's going to have very small strength of gravitational field, which is why it won't be able to attract Earth towards itself. However, there is a force between both. That is, this pen is going to exert a force on Earth, and the same amount of force will be exerted on Earth. The same amount of force will be exerted on the object by Earth. It is the same force, but that force is not enough to move Earth towards the pen, which is why the pen compensates and moves towards Earth itself. Which is why if you throw this pen, you're going to see it's going to fall towards the center of the Earth. That means there is gravitational field. And this region of space where you see the arrows, the attractive force, these denote the gravitational field lines of an object, in our case, Earth. So this region of space, if I highlight it, is the space of gravitational field. Every object is going to have its own gravitational field. The only difference is going to be its strength. How strong is the gravitational field going to be? In case of Earth, it's massive, which is why it gets to attract every object towards itself, right? So now, if I go ahead and take a few example of fields, gravitational field is not the only example. We also have electric fields. So if you study that topic, which you have to if you're studying A2 physics, you're going to see that there are electric field lines. That is, force applied due to one's charge. So in case of positive charges, what you'll see is the field lines are outwards. Why it is, you'll see in that topic. And in case of negative charges, the fields are inwards, that is attractive. So these lines denote the field line direction. However, what I mentioned in case of gravitational field is the field lines are always attractive. That is, it's always going to be towards the center of the object, always attractive, right? So if I leave an object over here, where is it going to go? Depending on the field line, it's going to move towards the surface of the Earth, right? Attracted. Now, in case of gravitational field, notice this is the surface of the Earth. We do know that Earth is a big sphere, but let's say when you're walking around a road, what you see is the road is straight, it's not curved. Now, that is due to the fact that Earth is so massive that you cannot notice the curvature with your bare eye. So that is also why this amount of length of Earth is going to seem like a straight line, which is why it's going to have a uniform field line. It's going to have uniform field lines because the mass is evenly distributed along the surface. We're considering it to be at least that the mass is evenly distributed. So the field lines are evenly distributed. The force at every point in this region on an object is going to be the same. So considering the mass distribution is uniform, we can say there is uniform field lines above the surface. So let's say you release a box, any object, what it's going to do is due to that gravitational field, it's going to fall towards the surface of the Earth. So that is due to the feature of gravitational field. Now, in case of the Earth itself, it is massive, and you're going to see it is a sphere, not a perfect sphere, but in our case, we're going to consider it to be one. And in that case, you're going to see the field lines are radial. I'm going to talk about it again, but the field lines are radial. When you consider the entire Earth, so let's say you go to outer space and start looking at Earth, it's going to seem like a perfect sphere, which is why the field lines from here to, let's say, to the surface of the Earth, it's going to make a 90 degrees. Even this one is going to make a 90 degrees. All the field lines are normal to the surface of the Earth. That means they meet at the center of the object. That is, in our case, Earth, right? Now again, gravitational force can only attract, not repel. Now, we understood what gravitational fields are in theory. Now, to understand what amount of force is going to be exerted on any mass, we have to understand Newton's law of gravitation. What does it say? The gravitational force between 2 point masses, the gravitational force between 2 point masses is proportional to the product of the mass and inversely proportional to the square of their separation. What does this mean? So, one by one, the gravitational force F, or call it Fg, force due to gravity, is proportional to the product of two masses. So let's say you have mass 1, this, and you have mass 2. So if you want to find out the force between both the masses, which is going to be equal to abide by Newton's third law, equal and opposite force. So therefore, this force Fg is going to be equal to this force Fg. So mass 2 exerts a force Fg on m1, and m1 is going to exert the same force on m2. So what did we understand from the first line? The force exerted is going to be proportional to the product of both the mass. That is m1 times m2, proportional to the product. Now the second part is it is inversely proportional to the square of their separation. So what is this separation? Remember, you're going to consider from the center of the mass. From the center of the mass, because when I was explaining the radial field lines, what I had mentioned is all of these lines seem to meet towards the center of the Earth, which is why we can consider the gravitational field is due to the mass at the center of the Earth, or the field lines are going to meet at the center of the Earth, which is why we can consider all of that gravitational field strength to be due to that point at the center. Now, since it is a perfect sphere, that is, we are considering it to be a perfect sphere, we can make this point mass approximation. Since in case of a perfect sphere, all the gravitational field lines seem to meet at one point, and that point we consider to be the center of mass, and that point we consider to be the point mass from which we are going to calculate the separation. Now, in case of a mass that is, let's say, not uniform, if the field line over here is going to be here, the field line over here is going to be here, field line, let's say, is somewhere here. So notice these are not going to meet at the same place. All of those are meeting at different places, which is why you cannot make that same point mass approximation. Anyways, coming back to our Newton's law of gravitation. So what we had figured is the force is proportional to the product of the two mass and inversely proportional to the square of the separation. That is the distance between the two masses. So from the center of M1, that is over here, and to the center of M2, that is over here. Now consider this to be the separation between both the masses, and it is going to be proportional to the square of the separation, right? So this is your Newton's law of gravitation. This is how you're going to find out what amount of force is exerted on any object, on any point mass. So let's say this pen or any other object, what is the force going to be? It's going to be m1 times m2, that is mass of Earth, mass of the object, divided by the separation between the center of mass of the object and center of mass of the Earth. So that is how you can find what amount of force is exerted on every object. Okay. So notice one thing. Both forces are Newton's action-reaction pair. That is, the force exerted is the same but in opposite direction, right? And the other thing is, again, no repulsion, only attraction, since field lines are always in one direction, that is towards its center. Right. Now, this describes the proportionality, right? However, the moment you remove that sign, you have to introduce a constant, right? Now, what is this constant going to be? So, experimentally, it has been figured out that it is going to be G, which is the gravitational constant, and the value of that is 6.67 into 10 to the power minus 11 Newton meter square kg to the power minus 2, right? This is going to be your gravitational constant. So every time you want to calculate the force on any mass, you have to use this constant. So your formula at the end of the day is going to be force is equals to gravitational force times product of mass divided by their square of separation. Okay, so I forgot to mention one specific thing about the point mass approximation. That is, I mentioned that we are considering a perfect sphere, that is, the mass is evenly distributed throughout the sphere. And in those cases, we can make the point mass approximation regardless of what distance the planet or sphere covers. That is, at what separation you are in comparison to the sphere or planet. In case of spheres that are not uniform in terms of mass, in those cases we can also make the same point mass approximation. That is, let's say it has the perfect shape, however the mass is not evenly distributed through the sphere. Now in those cases, what happens is, at large distances, what I've written in green over here, at large distances you can make the approximation, since until and unless you get really close to the surface, you're not going to feel the difference in mass distribution within the sphere or planet. So at large distances, even with non-uniform mass spheres or planets, you can still do the point mass approximation, since at large distance the influence of ununiform mass distribution is not going to affect the calculation. However, the moment you are close to the planet or close to the ununiform mass sphere, it is going to hinder your calculation, which is why in a lot of Mars schemes you will see it mentioned that this point mass approximation is viable for cases where there is a large distance or large separation between two planets, right? And in case of perfect spheres with uniform mass distribution, the point mass approximation seems to always work. So yeah, that's it actually for this video, and see you in the next one. Hey guys, welcome back to another video. In this video, we're going to talk about circular orbits in a gravitational field. That is, we know the moon is orbiting around the Earth, but why is it orbiting? How is it orbiting? And at what speed or at what rate is moon orbiting around the Earth? How can we calculate all those figures? So to do that, we're going to understand a bunch of things. First of all, we're going to recall that the force between two masses is going to be the same, the exact same. So let's say M1 is going to exert force Fg on M2. M2 is also going to exert the same force mg on M1. So the force is actually equal. Now, notice one thing. In case of circular motion, if you've already studied that topic, what is necessary for an object to be in circular motion or in a circular orbit is there needs to be a force that is perpendicular to your velocity, of the object. So let's say an object is at this instantaneous point is moving in this direction. There needs to be a force that is perpendicular to it. Now, when the mass moves over here and has a velocity in this direction, your force still needs to be towards the center and perpendicular to your velocity. So these few things need to be considered when you have circular motion or circular orbits in case of planets. So what's happening in our case is we have a moon orbiting around the Earth. Now, this force that is between both masses is going to contribute towards their centripetal force. That is, the force perpendicular to the mass's velocity. Therefore, the gravitational force is actually providing the centripetal force. Now, we know the formula for what centripetal force is. That is, we know Fc, centripetal force, is equal to mr omega squared. So we know the formula for Fc, that is centripetal force. We also know the formula from the previous video, that is of the gravitational field, force due to an object's gravitational field. So we know both of these formulas. Now, from these two formulas, can we figure out anything about the orbit of moon or any planet or any star around, not star, but any object, any mass around the Earth? Yes, we can. So if we equate both of these equations, that is Fc is equals to mr omega square, that is the centripetal force, and you know the force due to the gravitational field, G m, the product of mass divided by their separation square. So here is the Fg. We also know the circular motion's centripetal force. So we can equate both of these together, that is mr omega squared. M is the mass of the object that is orbiting. In our case, if you consider this to be the moon, the mass of the moon. So mr omega square, mass of moon, times the separation between the center of both the objects, and omega square is the angular velocity or angular frequency of the moon. At what rate is the moon revolving around the Earth? Right. And g(m)r square, g is a constant, mass of Earth is a constant, we know it, and mass of the moon is actually going to be cancelled off from either sides of the equation. And you have again the separation squared. So what you can do over here is you can make r cube the subject, that is, this r is going to go over here and it's going to give you r cube times this omega. You can break down as 2 pi by t, because you know omega is 2 pi by t, right? This is your formula for angular frequency from circular motion. You can also write it as omega is 2 pi f, but this is not going to help us over here. So we can write omega as 2 pi by t whole squared is equals to gm. Now what you can do over here is you can take everything on the other side, leave the r cube, and what you're going to have is gm times t square divided by 4 pi square. Now what this gives us is an interesting proportionality. That is, r cube is proportional to t square. What this means is the cube of their separation is proportional to the time period, proportional to the square of their time period. So this is actually Kepler's third law, but you don't need to understand Kepler's first and second law. Only Kepler's third law is going to be useful to you in this syllabus. Now, what this tells us about the orbit is if you increase the separation, your time period of the orbit is also going to increase. Therefore, if moon had a greater separation away from Earth, it would have a greater time period. And you can also say the opposite thing. So if it had a lower time period or a smaller time period, its radius would have to be smaller, right? So that's what we can understand from this proportionality. Now, that is what we understood from equating both the forces together. Now, let's say you want to understand at what speed is moon revolving around Earth. What is its velocity, right? In that case, what you're going to do is you're going to use another formula for centripetal force. Even in this case, notice the centripetal force is going to be given by your gravitational force. So your centripetal force you can write as mv squared, because you want to find the velocity of the moon. So mv squared by r, right? mv squared by r is your centripetal force, and your gravitational force is going to be gmm by r squared. So this is your centripetal force, and this is your force due to gravitational field. Now both of these are equal because gravitational field is actually providing the centripetal force, right? So if you equate both of these together, what you're going to see is if you make velocity the subject, you're going to have v squared over here, v squared, and you're going to cancel off one of the r's. So you're going to be left with, oh, by the way, you're also going to cancel the mass of the moon, right? So you're going to be left with the gravitational constant times the mass of Earth, and that is going to be equal to the square of velocity. So now if you want to make just the velocity the subject, you're going to have gm by r. So what we now understand is if you want to find the velocity of the moon, you have to know the gravitational constant, which you already know, the mass of Earth, which you might know if you just search, and the radius, that is the separation from the Earth's center to the moon's center. If you know that separation, you can find the velocity at which the moon is traveling. Now, there is something interesting about this formula. If you have noticed, in this formula of velocity of the moon, the mass of moon is not mentioned. So what this tells us is it doesn't matter how heavy or how large the mass of moon is, it is going to have the same velocity at the same distance away from Earth. So even if, let's say, moon was 10 kgs or moon was 1,000 kgs, it wouldn't affect its tangential velocity. It wouldn't affect its velocity at which it is revolving around the Earth. So its mass is not a factor, which is why the radius is actually going to determine at what pace, at what velocity moon is going to revolve, right? So your radius is the only factor because mass of Earth is not going to change. Gravitational constant is not going to change either. So your radius is going to be the factor over here. So different objects at different separation away from Earth is going to have a different velocity. Granted, the gravitational field is providing the centripetal force. Okay, so up till now, we understood Kepler's third law, the proportionality of radius, that is separation and time period. We also understood how to find the speed of any planet, any object that is orbiting around Earth. And we understood that mass is not a factor over there. The radius is going to determine at what pace, at what velocity an object is going to move around. So for this video, that is going to be it. And in the next video, I'm going to cover geostationary orbits. That is how satellites are able to stay where they are without falling towards the surface of the Earth or towards the center of the Earth. Why is it that they're able to maintain their fixed position above Earth? And how do we find their orbit? And how do we find at what distance, at what altitude do they need to be to maintain their orbit? So we're going to see that, understand about that in the next video. Hey guys, welcome back to another video. In this video, we're going to learn about geostationary orbits. Why are they useful? How do we calculate the altitude at which satellites need to be to maintain geostationary orbits? And how are they useful? So first of all, we need to understand the properties of a geostationary orbit. So the first point is a satellite, an object that is in geostationary orbit, it needs to be above the equator and it needs to be above one fixed point. So let's say I want a satellite right above this point in my room. So I'm going to place the satellite, let's say 800 meters or 1,000 meters above in altitude. And this is the point I fix to be the fixed point about which it is going to rotate or revolve around. So what's going to happen is as the Earth rotates, the satellite would rotate along with it in sync. It is not going to leave this fixed point. It is going to stay directly above this point and is going to revolve along with the Earth. Now, note one thing. This point that I mentioned, this fixed point needs to be on the equator. It needs to be on the equator. If it is in any other position rather than the equator, then it's not going to be in geostationary orbit. Why is that the case? Let's understand that. So if I have this tape, consider this to be Earth. I'm going to mark the top as North Pole, and the bottom as the South Pole. We do know that the Earth is actually a bit tilted, but let's not consider that and keep it simple. So I'm marking the equator. So south over here. So the North Pole is on top. Notice the North Pole is on top and the South Pole is at the bottom. And perpendicular to it is our equator. Perpendicular to it on the other side is our equator, right? Now notice one thing. If I revolve this Scotch tape around in that direction, what you're going to see is above the North and South Pole, it is rotating, right? Fair enough. So now let's say I have this marker, or let's take this this finger as the satellite, if I have this point marked as the fixed point, I'm going to keep my finger exactly above this point and I'll let the Earth rotate. Now notice, as the Earth rotates, I can keep my finger exactly above the fixed point. However, if my finger was at any direction other than the equator, let's say over here, this finger would rotate, let's say, in this direction, and the Earth would rotate in this direction. So notice, if I fix this top point as our fixed point, and I let the Earth rotate, and I let my finger rotate, they are out of sync. My finger is unable to be above the same exact fixed point. So mind you, yes, after a period of time, it will come back to the same fixed position, but it will not stay in sync. Whereas if I had fixed a point on the exactly above the equator, it would revolve around it exactly in sync. It would not move away from the fixed point. So if I show that on a diagram, that is, if I have this point as my fixed point, our satellite is going to revolve directly about this point along with the Earth. However, notice, if I laid it over here and say this is the circumference you have to oscillate, orbit, it will go out of sync from the fixed point because Earth is rotating in this direction. And if I let my satellite orbit in this direction, it is not going to stay in sync with the fixed point. So that is an important attribute of a geostationary orbit. It needs to stay exactly above the fixed point and it needs to revolve around along with the Earth, right? Okay, second point is it needs to move from west to east in the same direction as Earth. You already know that Earth moves from west direction to east direction. So let's say north is above, south is on the bottom, and north, south, west, east. For me, this side is west. For you, I don't know if this is west. No, this is east. So this is going to be your west. So consider this to be the west and consider this to be the east. So Earth is actually moving from west direction to east. How do we decide that? So if I'm thinking about this point, if this is my home or this is my country, this point, and this is, as I mentioned, the west side and this is the east side, what we notice is as the Earth moves from this direction to this direction, that is from west to east, the sun, let's say, is in this direction, the sun is going to rise from the east direction. So the sun rises from the east direction and the sun is going to set on the west direction, right? So this side of the Earth is going from west direction to the east, and we can see that the sun is rising on the east, and setting on west. This is why we can say that Earth, since sun rises on the east and sets on west, the Earth has to move from west to east to make that possible. So we know that Earth is also orbiting around something. That is, in our case, the star, the sun. So in our case, Earth is orbiting from west to east so that sun can rise on the east and set on the west, right? So taking that into account, we know satellite also has to move in the same direction to be above the same fixed point. So it has to move from west to east. Great. Third point, it has an orbital period equal to the Earth's rotational period of 24 hours. So notice, to be about the same exact fixed point, it needs to have the same 24-hour period. That is, it needs to complete one revolution within 24 hours so that it can stay about the same fixed point. Now, I keep repeating it needs to stay about the same fixed point, but why is that the case? Why do we need that? So let's say I'm transmitting any information to the satellite. Let's say I want the satellite to observe the weather. and I want the satellite to transmit that information to me. Now, the benefit of having it directly above you is there is no transmission delay. You don't need to figure out where the satellite is, calculate its distance, and then be able to take the transmit the information or take the information, receive the information. So no amount of tracking is required. So it removes the hassle, which is why it gets easier to monitor anything, the weather in a specific region or anything literally. So that is why having a satellite exactly above a fixed point is important, is helpful, right? So now let's look at a question. A satellite in geostationary orbit appears to remain above the same point on Earth and has a period of 24 hours. State two other features of a geostationary orbit. One, it remains directly above the equator, as mentioned, has equatorial orbit, and moves from west to east, as mentioned. So, okay. Now, one thing to understand is for this satellite to orbit, the satellite need to reach its velocity or orbital velocity such that Earth provides the centripetal force to revolve around Earth. We know from the previous video, Earth's gravitational field is going to contribute to the centripetal force. So the gravity itself is going to pull the satellite towards the center, providing the centripetal force. However, you may question, why is the satellite not falling towards the surface of the Earth? That is actually happening because the satellite at the beginning reached its orbital velocity. In case of circular motion, notice you need a certain orbital velocity to remain in that orbit. Similar to that, in our case, that satellite needs to reach the orbital velocity before it can continue its orbit solely dependent on the Earth's gravity. Therefore, there needs to be a thruster that provides that force and puts the satellite in that orbital velocity such that once that orbital velocity is reached, the satellite can orbit around Earth, since the Earth is going to provide the exact amount of force towards the center. So you have the two factors ticked off, that is in orbital velocity. Second, the centripetal force is provided by the Earth's gravity. Okay, so in this part we're going to see how the satellite, or at what distance the satellite needs to be to maintain geostationary orbit. That is, have the same period as the Earth's rotation, right? It needs to revolve along with Earth. So notice, for the satellite to remain in that exact orbit, it cannot be at any altitude. Because if you've watched the previous video, you've noticed that it needs to have a certain radius, sorry, not this one. It needs to have a certain radius to have a certain time period. So in our case, we know the satellite to remain in geostationary orbit needs to have a time period of 24 hours. So it needs to be at a certain separation away from the Earth's center such that this 24 hours of time period is achieved, right? So it needs to be at a certain altitude above the Earth's surface, right? So how do we find that? So we're going to find that using the Kepler's law. We found out that the R cube is equals to time period squared times gravitational constant times the mass of Earth divided by 4 pi squared. So now if you make time period the subject, you know the time period needs to be 24 hours. If you convert that to seconds, 24 hours into 60 minutes into 60 seconds, that is going to give you 86,400 seconds. So you also know the values for gravitational constant, you know the mass of Earth. So now you can find out the distance or the separation it needs to be at such that it can be in geostationary orbit. So you know the time period, you know the gravitational constant, you know the mass, and 4 pi squared is a constant. So now you will find for r, and you will see that that is the specific altitude you need for your satellite to be in perfect orbit or in geostationary orbit with respect to Earth, right? So this is the formula you can use to find the altitude or find the separation. Mind you, altitude is not the same as separation. I keep telling altitude, but altitude is measured above the Earth's surface, but the value you're going to get over here is from the center of the Earth. So if you are asked to find the altitude, in that case, you have to subtract the radius from it. Okay, anyways. So in this case, we were using the satellite as an example, which has a 24-hour orbit. 24-hour time period. Now, in other cases, you might be asked to find the separation needed given any time period. Let's say the time period for that is 100 hours. So in that case, you will be asked to find the separation. How will you do it? Same formula. So you're going to use 100 squared times g times the mass of Earth divided by 4 pi square, and you're going to get, if you take a cube root over here, you're going to get the radius or the separation for that object to be in orbit with a time period of 100 hours. So that's how you can find the distance. Now, there's an interesting part to this that I just added for no reason. You may think that, let's say, while playing cricket, let's say, for example, if you throw a ball, why doesn't it orbit around Earth? Why does it, fall towards the surface of Earth after a certain point? Whereas a satellite keeps orbiting. I sort of answered this in the previous part while talking about this, that it needs to reach a certain orbital velocity before it can continue its orbit around Earth. So even in this case, the answer to the problem is simple. When you're throwing the ball towards the stump, let's say, you're not throwing it with enough velocity. It's not that it is way too near the Earth's surface to maintain an orbit. It can maintain an orbit. But for that to take place, you need to throw it at a certain orbital velocity. So let's say we consider any ball to be thrown around the Earth's surface, near the Earth's surface, let's say. And what you're going to notice is you need to throw it at a certain velocity. Now, how do you find that velocity? Remember, from over here, the speed required to orbit a planet, in this part I had discussed. This is how you will find out the orbital velocity needed at that distance away from the Earth's center. So let's say I want to throw a ball from over here and I want this to orbit around Earth. Doesn't matter at what time period. I want it to orbit around Earth at this distance. So what I'm going to do now is, let's say the distance from the center of the Earth is going to be, I'm going to take the radius of Earth as the distance, and that distance is actually going to be 6,371 times 10 to the power of 3. That is your radius of Earth, most likely. Yeah, that is your radius of Earth. And 2, let's say I just considered it to be 2 meters above the Earth's surface. So, if this is your Earth, this is your radius, which I considered to be, or at the actual value is 6,371 into 10 to the power 3. And let's say I'm throwing the ball from this position, which is 2 meters above the surface. So I'm going to consider the radius. This is the radius. The separation to be 6,371 times 10 to the power 3 plus 2 meters. This is not actually going to do much of anything. But anyways, so I'm also going to take the gravitational constant, G. I'm going to take the mass of Earth, which is one search away. And now I'm going to find the velocity I need to throw the the cricket ball at, right? So now if I make velocity the subject, if I calculate all the values, what I'm going to get is 7,925 meters per second. That is 8 kilometers per second. So if I am at an altitude 2 meters above the Earth's surface, I need to throw that ball at a speed of 8 kilometers per second, which, mind you, is very fast. So if you have that amount of strength and you can shoot the ball at that speed, that ball is going to orbit around Earth's surface. Now, granted, we did not consider orbital decay, that is due to the air resistance. So we are not considering air resistance and any other factor. So granted, it is a void and there is no air resistance. If you throw it at 8 kilometers per second, it is going to orbit around Earth at an altitude of 2 meters. So I found this part a bit interesting, so I just added this over here. So yes, anything can orbit. If you can make it reach the orbital velocity, it is going to orbit around Earth. In an ideal situation, at least. Right. So, the next part I'm going to talk about is polar orbits. We started this video talking about geostationary orbits. In that case, the satellite needs to be directly above the equator, right? However, that's not the only kind of orbit. And that's not the only useful kind of orbit. We also need something called polar orbits. Now, what are polar orbits? Let's say this is North Pole, this is South Pole, and this is going to be a polar orbit. It's going to rotate along the axis of North and South Pole. While beginning this video, I took this example and said how if I take a point and I make it orbit, it is going to orbit out of sync. It is not going to be about the same fixed position. So in polar orbits, the difference is it's not going to be about the same fixed position. It's not going to stay above the same fixed position, right? That's the first point. So yeah, it is an orbit where the satellite is going to orbit about the axis of both poles, that is North and South Pole. So it's going to, if this is your North Pole and this is your South Pole, it's going to orbit like this. It is going to orbit like this, right? Okay, so it is not a geostationary orbit, meaning it doesn't stay above a fixed position. As mentioned, it does not rotate around the equator. It rotates around the axis of rotation. Okay, so it tends to orbit at lower altitude. That is third point. Fourth point, the time period is going to be lower. Why? No, remember the formula proportionality that r cubed is proportional to t squared. So if your altitude is lower, your time period is also going to be lower. So in polar orbits, the altitude is lower, the time period is also lower. Now the benefit of this is, since the satellite is at a lower orbit, you can transmit the information a bit faster, since it doesn't take as long to reach that altitude above Earth's surface. In case of equatorial orbit, we saw that it needs to be at a certain height above the Earth's surface to maintain that orbit. Although, yes, it's directly above your fixed point, you do not need to find out where it is, but that amount of time needed to transmit the information might cause a lot of information loss, a lot of data loss, which is why it is also beneficial to have polar orbits where the orbit is actually lower, where the information can travel faster. Even though you need to track where the satellite is, you can transmit the information a bit faster. And there is less likelihood of data loss. Okay. So if we try a question over here, suggest one advantage and one disadvantage of the use of geostationary satellites compared with polar orbiting satellites for communication between points on Earth's surface. So the advantage of using geostationary satellite is one, as mentioned, no tracking is required, since the satellite stays directly above one point on the equator and it orbits with the same speed, with the same angular frequency as Earth. So you don't need to do any bit of tracking. The disadvantage though is the orbits are longer, hence further from the Earth's surface, because the orbit is 24 hours, right? So it is further from the Earth's surface, the separation is much bigger. Therefore, there is a larger delay or greater attenuation. You're not going to understand what attenuation is, but just understand there is a greater delay of information being transmitted from the Earth's surface to the satellite, because the time period is very large, 24 hours. So the separation, the altitude the satellite is at is also very large, which is why there is a lot of data loss, or a lot of time is required for the data to be transmitted. Whereas if it is a polar orbit, it has a lower time period. We set the time period to be lower and keep it at a lower altitude. The benefit of that is we can transmit the information faster. So those are the 2 points, and that is what geostationary orbits are. And that is it for this video. See you in the next one. Hey guys, welcome back to another video. In this video, we're going to talk about gravitational field strength. Up till now, we learned about how to find the orbital velocity, how to find the force between 2-point mass, and what different types of orbits are: polar orbits, geostationary orbits, and how to achieve those orbits. We also learned about Kepler's law, how radius and time period varies. And in case of orbits, we learned how circular motion is related to gravitational force. Now, in this case, in this video, we're going to learn about gravitational field strength. That is, for a specific point mass, let's say this mass, this planet, what is its gravity or gravitational field strength going to be? Now, near the surface, it is going to have a specific gravitational field strength, that is a set amount of force per unit mass, and at a different distance, I'll mark it with orange, at a different distance away from the point mass, it's going to have a different force per unit mass. That means different gravitational field strength, a different gravity. Now, in our case, we have always heard that gravity is set to be 9.81 in case of Earth. But it turns out to be that as you move away from a point mass, in our case, considering the planet Earth, as you move away from it, that is, as the separation increases, the gravity turns out to decrease, which means with varying distance, with varying separation away from the point mass, your gravity or gravitational field strength will decrease. Now, to understand that better, let's define what gravitational field strength is, right? So, gravitational field strength at any point is defined by the force per unit mass. Therefore, if this is your point mass, at any given distance, what is the force per unit mass exerted? Therefore, if I have 1 kg object over here, that is 1 meter away from the point mass, what is the force going to be exerted? And at this distance, 2 meters away, what is the force going to be exerted? And at 3 meters away, what is the force going to be exerted on, mind you, 1 kg of mass? Because it's talking about gravitational field strength per unit mass. So we're going to think of this in terms of what force is exerted on 1 kg of an object due to any isolated mass. In our case, let's talk about planet Earth, right? So what is the force per unit mass at any given distance? That is what gravitational field strength is. Now, how can we derive gravitational field strength? So in this part, we'll talk about deriving the formula of gravitational field strength. Now, let's take 2 masses. One is M1, consider it Earth. The other is M2, consider it anything, any rock, or let's say moon. So these 2 masses are affected by each other's gravitational field. That is, we will have a gravitational field that is inwards for M1. You have another gravitational field that is inwards for M2. Now, what happens is both of these gravitational fields interact, and both of these pull the other mass towards its center. So M1 is going to pull M2 towards its center, and M2 is going to pull M1 towards its center, right? Now, what that at the end of the day results in is a net force, a net gravitational force, Fg. This Fg turns out to be the same for both masses due to Newton's pair of force. Action force is equals to repulsion force, so that is Newton's third law, right? So that is a weight over here, since Fg on M1 is the same as Fg on M2. Now, taking that into consideration, let's derive our gravitational field strength. Now, you know two formulas. That is, one is of Fg. In the first video, we talked about how Fg equates to Gmm by r squared. So gravitational force is given by this formula. You also know another formula, which is F is equals to mg. This is something that we have learned from a very young age. The net force on any object, be it this pen, be it the mouse, be it anything, is going to be mass times the gravity or the gravitational field strength. This G denotes gravitational field strength. Therefore, at the surface of Earth, we all watching this video are at the surface of Earth. And at the surface of Earth, there is a specific gravitational field strength near the surface, that is. So this G denotes that gravitational field strength. So mass times gravitational field strength, in our case near the surface, is 9.81, gives you the force, the net force. So if we make the gravitational field strength the known formula, the subject, right, we're going to get F by M, right? This is one of our formula. So let's take this into account. And the other formula, as mentioned, of Fg, let's take this into account, right? So both of these formulas, you know, and what I'm going to do next is I'm going to equate this formula and this formula. F is equals to mg. This is the mass m2, let's say the moon, times gravitational field strength of the mass of Earth, that is the field strength due to the mass of Earth. So at this given distance, what is the gravitational field strength of Earth? That is denoted by G. So G times M2, the mass of moon, is going to give you the gravitational force. Great. So now you'll equate equation 2 in this part. Now what you're going to get is Gm is equal to Fg Gmm by r square. So you have equated the two force formulas known to you, and what you get at the end of the day is the formula for gravitational field strength, Gm by r square. That is the mass of Earth, whose gravitational field strength you're measuring, divided by the separation at which the object is, the m2 mass is. Therefore, gravitational field strength is given by the gravitational constant times the mass of itself divided by the separation squared. Now, there was a simple way to do this. That is, if you had taken the net force, that is Gmm by r square, and just plugged in the value m is equals to 1 kg, you would have gotten the GFS formula, Gm by r square. Because remember, what the formula tells you is gravitational field strength is the force per unit mass. It is still the force, but with respect to 1 kg of mass, right? So, due to the gravitational field of Earth, what is the force going to be exerted on 1 kg of mass? It is going to be given by this formula, Gm by r square. So let's say you're 2 meters away from Earth. What is the gravitational field strength at that point? It is going to be Gm by 2 squared. And if you know the gravitational field strength, and if you know the gravitational constant, and if you know the mass of Earth, you can find out the gravitational field strength due to the Earth's mass, right? So this is how you can figure out the gravitational field strength at any given position. Notice the separation, the radius away from the center of Earth is going to affect your gravitational field strength. And we are going to see how the effect varies with different separation. Great. So we understood the formula of Gm by r square. The same could be done with the mass of Moon. So using the mass of Moon, you could find its gravitational field strength. So you would have plugged in for the gravitational field strength of Moon. What you would do is the gravitational constant mass of Moon, that is m2, divided by the separation at which the Earth is. Now mind you, this would actually give you a lower value compared to the gravitational field strength of Earth. Now you may be confused that isn't the force Fg supposed to be the same in both cases? Yes, it is supposed to be. Because in our case, what you have found out using the formula is the field strength, not the net force. So the moment you multiply this gravitational field strength with the mass of, let's say, Earth, m1, you will get the net force. Similarly, in this case, the moment you multiply this g with the mass of Moon, you will get the same Fg. So therefore, Newton's law of gravitation does not get disobeyed, right? So next up, we're going to learn about the gravitational field strength at the planet's surface, in our case, Earth. So we're going to see what the gravitational field strength is near the surface of Earth, right? Now, we already know the value G is equals to 9.81. Let's see if we do get this value, right? So now we know the formula of gravitational field strength, which is G times mass of Earth, the field strength of which we want to find out, and the separation. Now, in case of the separation, remember, we measure from the center of Earth, or the center of the mass. Now, the center of mass turns out to be over here, and this value is going to be the radius. And let's say you want to find out the gravitational field strength at a small distance above Earth. Let's say 2 meters above the surface, right? So what you're going to do is gravitational constant times the mass of Earth divided by r, the radius of Earth, plus the altitude at which you're measuring the field strength to the power of 2, right? So now, after you plug in all the values, what you're going to see is, since the h, the altitude that you're taking, let's say 2 meters above the Earth's surface, is very small compared to the radius of Earth, which is actually really big. Now, compared to that, since it is so small, we are going to say r plus h is approximately the same as only r, since the h is not going to vary the amount, right? So in that case, we can write Gm by r squared, in which case the answer turns out to be 9.81 newtons per kg. If you want to find it out yourself, you can plug the values of gravitational constant, you can search the mass of Earth, and you can search the radius of Earth. And what you're going to see is the gravitational field strength turns out to be 9.81. Right. The other thing to note is we have taken a small value of altitude or a small value of h over here. Now, in the case that you are really far away from the surface of Earth, in that case, your h is going to actually affect the separation, the net separation, which is why the gravitational field strength, the gravity at that separation is going to change from your known value of gravitational field strength, that is 9.81. The other thing I want to mention over here is the amount of gravity or gravitational field strength is actually different at the North Pole and on the line of equator. Now, why does this happen? The reason is, compared to the North Pole, notice this image over here, our Earth is actually a bit bulged in terms of on the line of equator. What this means is the shape of Earth is actually a bit flattened. What this means is if this was a perfect sphere, North Pole or the point of North Pole would have been over here. Now notice there is a difference in height, right? Now this causes the value of gravitational field strength to change over here. And why does that happen? Notice this point is closer to the center of Earth. So what that results in is your R square value, the separation squared, decreases. And what that results in is the ultimate gravitational field strength value to increase, which is why the gravity at the North Pole is higher than the gravity on the equator. So this is how the radius ends up affecting the value of gravity or gravitational field strength. Great. Now the other thing, I've partly already explained this, but the question is, why is G, gravity, constant near the surface of Earth? Now if you look at this diagram, if you compare this, consider this to be Earth, notice if you're really far away from Earth, the Earth would look like a normal round sphere, right? Which is why its gravitational field lines are supposed to be radial and be 90 degrees to the surface, meeting at the exact center. So it is supposed to have non-uniform or radial field lines. Notice the spacing between the field lines increase as you move away from the surface of Earth. Now what happens is, when you're really close to the surface, you cannot notice this curvature. You cannot notice that Earth is round. For example, if you go out on a walk, you're not going to notice the arc of Earth. You're not going to notice the curvature of Earth with your bare eyes, because Earth is massive, which is why the surface seems to be exactly straight, which is also why the field lines near the surface can be considered to be uniform, because it seems as though the surface is quite straight. And that is also why your field lines turns out to be approximately uniform, which is why up till a certain height above the surface, your amount of gravity or gravitational field strength does not change, because the field lines have uniform separation as you move away from the surface. Therefore, the field strength does not change much with small increase in height or altitude. Therefore, due to uniform field lines near the surface of Earth, your gravitational field strength stays approximately equal, which is 9.81, right? The next thing we're going to talk about is how does gravitational field strength change as distance / radius varies. That is, if you have planet Earth over here, this is your center, this is your radius. Hey guys, welcome back to another video. In this video, we're going to learn about gravitational potential energy. Now, up till this point, we learned about how the force varies with different distances away from Earth, and how the graph looks like inside Earth and outside Earth. And we saw that as you move away from the surface of Earth, the force per unit mass actually decreases. That means the gravitational force decreases with increasing distance. Now, in this video, what we're going to learn about is gravitational potential energy. You might have already studied this in O-level or previously. And in those cases, what we used to do is we used to consider the gravity to be constant, right? We used to consider gravity to be 9.81. And that is All right, considering you're taking the height, the change in height to be near the surface, that is, the change in height is very small compared to radius of Earth. And I talked about this in the previous video, where the change in height or the height is so small compared to the radius of Earth that it does not change the ultimate value of force. Which is why you can use this formula that you used to do for positions that are close to the surface of Earth, right? In those cases, it's not going to change your gravitational potential energy. Now, what we used to see is, let's say, this pen. I'm lifting this up to a distance of 1 meters. I am putting in energy into the pen. And what we used to get is, let's say, after lifting it by 1 meters, it gains, let's say, this 100 grams of mass, 0.1 kg, times gravity 9.81, times the height 1 meters. It's supposed to give you 0.98 joules of energy. What this tells you is the pen has gained 0.98 joules of energy as its potential energy. Now, that statement is actually correct, that it has indeed gained 0.98 joules of energy as it moved from this position to this. That is this is not 1 meter, but this, right? It has gained 0.98 joules of energy. That is absolutely correct. But if you frame the statement as the gravitational potential energy of this pen after being lifted by 1 meters is 0.98 joules, then the statement is wrong. Because gravitational potential energy is actually always negative. And that is an interesting thing that we're going to discover in this video. Why is it negative? And why is the statement that its gravitational potential energy is, let's say, 0.98 joules wrong? You are indeed putting in energy and giving it 0.98 joules of energy in the form of potential energy, but that is not its ultimate potential energy. You have provided that energy, but that is not its potential energy, the net potential energy. So, one by one, let's start from how we used to define gravitational potential energy. That is, we used to say gravitational potential energy is the energy of an object when it has been lifted off the ground through any distance. The amount of energy it will have relative to its height above Earth. So we used to say gravitational potential energy is mg till h. Again, considering g is constant, that means near the Earth's surface. Now, what this used to consider is near the surface or on the surface, the amount of work done or the amount of potential energy the object has is 0. And the moment you lift it up by 1 meters, it gains 0.98 joules. However, that is not really correct. I mean, it gains 0.98 joules, but at the surface, it doesn't have 0 joules of potential energy. It actually has a really large negative value of potential energy. Why does that happen? Let's see. Now, this is a way you can define gravitational potential energy in general, but this is not how you're going to write in the question paper. I'm going to show you what the real definition is. But you can say the gravitational potential energy is the energy an object possesses due to its position in the gravitational field. That is, let's say I have an object here, and relative to the position of this object, if it is near to the Earth's surface, it's going to have a specific potential energy. If it is farther away from the surface, or I mean from the center, sorry, I keep saying surface, not surface, center. If it is farther away from the center of Earth, that means it will have a different potential energy, right? Therefore, relative to its position, it's going to have different gravitational potential energy. Now, let's say from the surface of Earth, if you are lifting this object up, you're doing work on the object. You're putting in energy into the object for it to be lifted up by any change in distance. Now, the heavier the object, the greater amount of energy you need to do. So therefore, we know that we are increasing or putting in work into the pen to lift it up by a distance. Therefore, we're putting in energy. We are doing positive work done on the object. Now, what we used to consider is at the surface, the energy is zero. However, that is wrong. Why? Because notice, at infinity, at a distance that is at infinity, in that case, the amount of work done on the object is going to be zero. Its gravitational potential energy is going to be zero. Why is that the case? It's because at infinity, there is no gravitational field strength of the Earth. Because at infinity, the field lines of Earth are so far away that at the end of the day, no amount of force is exerted on an object that is infinitely away from Earth. So, at infinity, mind you, no amount of force is being exerted on the object. Therefore, the energy the object will possess is zero. The energy the object will possess at infinity is zero because no amount of force is being done on that object. However, at the surface, if you consider the energy to be zero, you cannot increase the value from 0 to 0. That is, you cannot do positive work done and transfer your own energy to the object and increase it to 0. That is not possible. So, granted, we understand that at infinity, the gravitational potential energy is 0. We can say near the surface, the gravitational potential energy has to be negative. The potential energy near the surface has to be negative. Why? Because only if the potential energy near the surface is negative, will it increase to a potential energy of 0 at infinity. At infinity, it will increase to 0. That means when it has a potential energy of 0, it is outside the gravitational field of Earth. That means it is not under the influence of the gravitational force of Earth, right? The other way to think about this is as you move from infinity to closer to Earth, it loses its energy. Why? Because you're not doing work on the object to bring the object near the Earth's surface. The Earth is doing the work. The Earth is pulling the object near the surface. So you don't have to do anything. Therefore, the object will lose its energy from 0 to a negative value. So now, again, from near the surface, if you want to push it away, you will provide energy and increase it to 0. And from infinity, if it comes closer to the surface, that means it's losing its energy. So from 0, it goes to a highly negative value near the surface. Therefore, the first thing we learned, and first thing we have understood over here is at infinity, the gravitational potential energy is 0. Near the surface, the gravitational potential energy is negative. And since it is attractive force, that means in case of attractive forces, the gravitational potential energy is always going to be negative. Because bringing an object from infinity to a point near the surface, you don't need to do any work. The work is done by gravitational force. Since it is attractive force, so you don't need to work against the force to bring it closer to the surface. However, when you take it away, move it away, you need to provide or transfer energy, in which case positive work is done. And bringing it from infinity to near the surface, negative work is done, because the work done is by the gravity of the mass. Therefore, the gravitational potential energy is always what? Negative, right? So that is the main purpose of this whole explanation, that near the surface, gravitational potential energy is negative. And always the gravitational potential energy is negative. Great. So now, how can we define gravitational potential energy? The exact definition is going to be, it is the work done in bringing an object or a mass from infinity to a defined point. So let's say the amount of potential energy that object A is going to have is the amount of work done that Earth did in bringing this object A from infinity to this defined point. That is how gravitational potential energy is defined. Therefore, near the surface, the gravitational potential energy will be highly negative, because bringing it from infinity to this point near the surface, a lot of work was done. Because near the surface, remember, there is higher amount of force. Therefore, greater work was also done, right? So as you move closer to the Earth's surface, force increases, which is also why amount of work done increases. But remember, potential energy is negative. Therefore, near the surface, a highly negative value of the object's potential. Therefore, again, the definition of gravitational potential energy is going to be the work done in bringing a mass from infinity to a defined point near the mass. From infinity to a point. Any defined point, anywhere. That is going to be your work done, and that is going to be your potential energy, right? So this is the definition. And the formula for gravitational potential energy is actually Gmm by R. Now, you may be confused by the formula of force and formula of gravitational potential energy. To make it clear to you, an easy way to remember this is Fg, force is Gmm by R squared. So the difference between both is, in case of force, the radius, the distance has a power of 2. In case of potential energy, the radius does not have any power. Therefore, Gmm divided by R, and there is a negative sign in front. Why? Because negative work is always done in bringing it from infinity to near the surface. Therefore, this is your formula for gravitational potential energy. You don't need to know how the formula is derived. However, if you are interested into knowing how GPE, gravitational potential energy of an object, the formula is derived, I will show you over here. So, from the last video, you know the graph of gravitational field strength. Now, I had also mentioned that the same shape of the graph is going to be for the force versus distance graph. It's going to be the same shape. So, if we take that into account, remember, near the surface, radius of Earth. So, if this is the center of Earth, this is your Earth, this is the surface, this is a defined point R at which we want to find the gravitational potential energy at, and this is infinity. So remember the formula of gravitational potential energy, the amount of work done in bringing an object from infinity to a defined point, let's say R. So what is the gravitational potential energy of the object at this defined point R near Earth, near the mass, right? So remember the formula for work done, force into distance. So what you have over here is force on the y-axis and distance on the x-axis. So how will you find out the work done? You integrate. You find the area under the curve between r and infinity. That's how you're going to find the formula for gravitational potential energy. Therefore, from infinity to r, let's integrate. So you know the formula for force, Fg, and you're taking the upper bound as r, lower bound as infinity, because you're going from infinity to r, right? Great. So you're integrating with respect to r, because it is a function of r, gmm by r square, right? And this shape of the curve again is due to this proportionality of 1 by r square. Okay, so now to find the gravitational potential energy, if I integrate both, what you're going to have is this. For integration of Fg from infinity to r is going to give you the gravitational potential energy. Mind you, this is actually the sign for gravitational potential energy. This is how you denote gravitational potential energy, right? So for gravitational potential energy, integrate gmm by r square, the force from infinity to r. Take the constants out of the integral sign because constants don't affect your integration. And what you can do now is integrate. How will you integrate 1 by r square? Very simple. It's going to be 1 by r to the power minus 2 plus 1 divided by minus 2 plus 1. It's going to be r to the power minus 1 divided by minus 1, which is going to be minus 1 by r. So this is your integration. Minus 1 by r. Does this match? Yes, it does. Minus 1 by r is your integration. Now you have to input the bounds, upper and lower bounds, right? So once you plug in the upper and lower bounds, it's going to be 1 by r, the defined point, minus 1 by infinity, right? This is going to be your value expression. So 1 by infinity is infinitely small, therefore we can write it as 0. So what you have over here is minus gmm by r. So this is how you get the formula for gravitational potential energy. This is the work done bringing the object from infinity to a defined point r, right? Right. So this is your formula for gravitational potential energy. Okay, so in this part, we're going to see the difference between the previous and the derived gravitational potential energy formula. So I've already mentioned this towards the beginning of the video, that in case of MGH, that is the formula we used to use previously, the gravitation, the G value, the value of gravity, was actually a constant that is near the surface of Earth. The value of gravity is the same. Granted, the change in altitude is very small, right? In that case, this formula is, it makes sense because gravity stays constant. So change in height is going to give you the change in potential energy of the object. Now, mind you, this formula is accurate in terms of giving you the change in gravitational potential energy, which is the purpose of this formula, to find the change in gravitational potential energy. Now, what the formula that we have is the net gravitational potential energy of any object, that is bringing it from infinity to a defined point. At that point, what is its gravitational potential energy, right? Now, this equation is also derived from this complicated equation. How was it derived? Let's see. So for the change in gravitational potential energy, what does it mean? It means it goes from, let's say, near the surface of Earth to a position that is away from the Earth. So let's say it was initially at a distance 1 meter away from surface, and then it went 3 meters away from the surface. In those examples, notice it is moving away. Therefore, you're giving or putting in work into the object. You're transferring your energy into the object. Therefore, what we will do is find the gravitational potential energy at the final position, that is moving away from Earth, and the initial gravitational potential energy, right? So final minus initial gravitational potential energy is going to give you the del U, or change in gravitational potential energy. And we're going to see how this formula is derived, or this approximation is derived, right? So finding that out over here, the final gravitational potential energy is going to be minus G, mass of Earth, times mass of the object, divided by radius of Earth, that is up till the surface, plus the height that you lifted the object by, that is h. Meaning this height, change in height, is actually quite small compared to the radius of Earth, because we are considering, in this formula, we're considering the g to be a constant. Therefore, taking that into account, let's continue. That is final minus initial. So the initial will also have another minus sign, gmm by r, right? Now, as you open the brackets, gmm, by the way, initial means near the surface of Earth. So on the surface, the distance from the center is r, the radius. So r plus h plus gmm by r. Now, taking the constants out of the equations, therefore minus 1 by r plus h plus 1 by r. Great. So now, notice, if I do LCM over here, what's going to happen is we're going to have r times r plus h, and then we're going to have minus r plus h. Fair enough. So what we're going to be left with is this r and this r is going to be cancelled off, and we'll be left with h divided by r times r plus h, right? So now we can consider, remember, we consider the height to be small compared to the radius of Earth, right? Why is that? Because we are considering the gravity to be a constant, in which case we can say r plus h is actually similar or approximately the same as the radius of Earth. Because let's say if you have a distance of 3 into 10 to the power of 6 plus 3 meters, is the 3 meters going to affect your overall distance? No, it's not going to. It's not going to affect your gravitation, which is why we can say r plus h is r. So we can say gmm divided by h by r square. Gmm h by r square. Now remember the formula for gravitational field strength, right? The formula for gravitational field strength was gm by r square. So take that away, and you're going to be left with g times mh. The gravity, not the gravitational constant, I mean gravitational field strength. Gravitational field strength times mass of the object times the height, the change in height. The change in height. So this is actually going to give you the change in gravitational potential energy. Therefore, this is how we get, this derivation is how we get the formula for mgh, right? Fair enough. So in this video, that is all I'm going to talk about. So we learned about the formula for gravitational potential energy, and we learned about how mgh was derived, and what it means to have a negative gravitational potential energy. So I'm going to keep it there. And another thing I'll add though is, notice this is how we derived, this derivation is how we derived the formula for gmh, that is, mgh, better known as mgh. So this is how we found out the change in gravitational potential energy for distances near the surface, right? Now, in the case that you are really far away and you cannot make this approximation that r plus h is actually equal to r, in those cases, what you're going to do is find the gravitational potential energy of the final position, that is, be it near the Earth's surface, be it away from the Earth's surface, does not matter. Find the final position. So if this is Earth and this is point B and point A, if you're going from point B to point A, find the gravitational potential energy at point A minus the gravitational potential energy at point B. So what this is going to give you is the net change in gravitational potential energy, and it is supposed to be positive because you're moving away, right? You're putting or transferring in energy to the object. Therefore, in that case, the change in gravitational potential energy will be positive. And in that case, you're going to use the formula minus gm m by r minus gm m by r2 r1, right? This is how you will find out the change in gravitational potential energy if the change in change in separation is really large, right? In those cases, use this formula. And I'm going to again talk about this in the video for gravitational potential, right? So see you in the next video. Hey guys, welcome back to another video. In this video, we're going to talk about gravitational potential. Now, this is actually similar to the topic gravitational potential energy. The thing with gravitational potential energy is it just talks about the amount of work done per unit mass. That is the only difference in case of gravitational potential, right? So if you look at the definition of gravitational potential, it is the amount of work done per unit mass in bringing a mass m from infinity to a defined point. Therefore, it is talking with respect to a mass of 1 kg, the amount of work done in bringing it from infinity to a defined point for that 1 kg of mass, right? So in case of gravitational potential, since we're talking about 1 kg of mass, right, we're going to divide the gravitational potential energy, that is gmm by r, divided by the mass of the object, and you're going to be left with negative gm by r. That is going to be your formula for gravitational potential. The other way to think about this is minus gmm by r. If this was your formula for gravitational potential energy, consider the mass of the object to be 1 kg, and you're going to be left with phi, or the gravitational potential energy, which is minus gm by r. Therefore, this is how you get the formula for gravitational potential, the amount of work done per unit mass in bringing it from infinity to a defined point, right? So this is the formula and definition of gravitational potential. Now, why gravitational potential is actually needed? Because it makes everything uniform in the sense you know the amount of energy needed with respect to 1 kg of mass for all examples. Let's say if you have a planet this big and you have a planet this big, both of these are going to have different gravitational field strength. So they're going to have or exert a different amount of force on every object, right? So when you have the amount of energy needed or the amount of potential of an object at any given position near the Earth's surface or another planet's surface, if it is in terms of 1 kg, you can compare it with different examples, different planets. So it makes it easier. And the other thing is, once you know the potential, you can calculate the gravitational potential energy for different masses. So phi, gravitational potential, times the mass of any object is going to give you the gravitational potential energy of that object. So 2 kg of mass will have a different gravitational potential energy, and a 3 kg of mass will have a different gravitational potential energy, which is why having the gravitational potential is important, right? Okay, fair enough. Now again, why is the gravitational potential negative? Because remember in the previous video, I talked about how when you're pushing an object away from the Earth's surface, you're actually exerting force and putting or transferring in energy from yourself to the object, right? And you know, at infinity, the amount of energy the object will have is zero. Why? Because it is out of the gravitational field of the planet. Therefore, you have increased its energy from a negative value to zero. Because if it was positive near the Earth's surface, it couldn't increase to zero, right? So near the surface, the value is negative, and you increase it to zero at infinity. You transfer energy to the object until it reaches potential energy of zero at infinity, right? So therefore, near the surface, gravitational potential is negative. The other way to think about this is whenever you have attractive forces to objects. Okay, I have an example over here. Right. Whenever you have attractive forces, the gravitational potential, or in case of charges, the electric potential EP is always going to be negative. Because the work is done by each other. You don't need external energy. You don't need external force. In case of two negative charges, they have repulsive force. In that case, I need to externally push the charges towards each other. So they will have a high potential because they want to break away and move away from each other, right? In that case, they have a high positive potential, right? So whenever they're near each other, right? In case of masses, in case of positive and negative charges, where there is attractive force, the potential energy or electric potential or gravitational potential is going to be negative since attractive. Now, the other thing, what is change in gravitational potential energy or the change in gravitational potential? I talked about this in the previous video towards the end. That is, to find the change in gravitational potential energy, what you do is take the change in gravitational potential energy as the final gravitational potential energy minus initial gravitational potential energy, right? So you can plug in the values as minus gmm by R2 plus gmm by R1. Granted, R2 is your final position and R1 is your initial position, right? Is R2 my final position? Yeah, R2 is my final position over here and R1 was my initial position. So I'm moving closer to the surface of Earth, right? In that case, you're going to lose energy because you're going from a less negative gravitational potential energy to a more negative gravitational potential energy, right? So you're losing energy. Therefore, you can next take gmm common, and what you're going to have is gmm times 1 by R1. Is it the final? No. This is the initial position minus 1 by R2, the final position, right? So this is how you can find out the change in gravitational potential energy. The final gravitational potential energy minus initial gravitational potential energy. Now, how to find the gravitational potential, that is amount of work done or unit mass? Simple thing, you plug in the value 1 in place of the small m and you will be left with change in gravitational potential, not energy. Therefore, you can also do the opposite. If you know the change in gravitational potential, just multiply the mass of the object and you're going to get the change in gravitational potential energy, right? Great. So this is how we find the change in gravitational potential energy or change in gravitational potential. So that sums it up for potential energy, and that is actually it for this video. See you in the next one. Hey guys, welcome back to another video, and this is going to be the last video in this series, that is for gravitational fields. And in this video we're going to talk about astrodynamics. This is actually sort of my favorite topic, and this is something in general I do want to study about eventually. So what this talks about is, first, let's understand the energy of different objects due to its position in the gravitational field. Now, the thing is, for all the planets out there, it tends to orbit around, let's say, a star or a planet. In case of Moon, it is orbiting around Earth. In case of Earth, it is orbiting around Sun, right? Everything turns out to be orbiting around something. So it has a certain velocity. Therefore, it has a certain kinetic energy. However, it is also under the influence of gravitational field of the object around which it is revolving, right? So in case of Earth, it's revolving around Sun, right? In case of the satellite we talked about in geostationary object video, the satellite is orbiting around Earth, right? Therefore, every object over here has a certain kinetic energy, and it has a certain gravitational potential energy due to the gravity acting on it. And there's an interesting question that how can you escape the gravitational field of any planet, any star? The easy answer to it is give it enough kinetic energy. If you give it enough kinetic energy, it will break free of the gravitational field strength and be away from the gravitational fields. The gravitational fields will no longer have any effect over the planet, over the object, over the mass, because it has enough kinetic energy to escape from it. And in case of that kinetic energy, it needs a certain velocity, which is known as escape velocity. So those are the things we're going to understand through different parts in this video. First up, we're going to understand the kinetic energy of satellites, right? Now, we know from previous videos that V square is equals to Gm by R. If you don't know where that came out of, here's the quick recall of it. So basically, in case of a satellite revolving around Earth, its centripetal force is provided by the gravitational field or the gravity of Earth, right? The gravitational force. Now, in that case, the centripetal force mv squared by r is provided by the gravitational force. Now, we want to understand or know the speed of, the orbital velocity of the satellite. So what we do is use this formula of centripetal force and make v squared or v the subject. So what we get from there is v squared is equal to gm by r, right? Now, to find the kinetic energy of the satellite, what we can do is we know the formula of kinetic energy, that is half mv squared, and you know the value of, or the expression for v squared, that is gm by r. Plug that in over here, and what you're going to have is ke is half times gm m by r, right? Fair enough. So that is its kinetic energy. Now, let's figure out its gravitational potential energy due to its position in the field of Earth. In that case, we're going to have minus g m by r. This is the gravitational potential energy of the satellite. Now, can you notice something interesting over here? That is, the kinetic energy is exactly the half of the potential energy, the gravitational potential energy. And this is actually going to be quite useful later on in this video. So, what both of these figures mean is, if I have this object rotating, revolving around Earth, it has a certain kinetic energy, half gm m by r, and its potential energy, meaning the work done that was needed in bringing this pink object from infinity to this point was minus gm by r, right? From infinity to this point, I needed minus gmm by r worth of work done to bring it from that point to over here. Therefore, if I want to do the opposite and take it from this orbit or from this position near the Earth's surface or near the Earth to infinity, I need to provide positive gmm by r. How will I do that? I will, let's say, do extra work on it. I'll provide it with my energy. I'll provide it with my energy and provide the exact amount as gmm by r, such that it will go to infinity. And you know, at infinity, the potential energy or the field strength of Earth is going to be 0 because it is infinitely away. Therefore, at that point, no field strength, therefore no gravitational potential energy. Therefore, it is free of Earth's gravity, right? It has escaped Earth's gravity. So let's work with that idea. So we can figure out the total energy of the satellite at this point. It has this kinetic energy and this potential energy. So the ET, that means E total, is going to be half gmm by r minus gmm by r. What that results in is the total energy of the satellite is minus gmm by r, or you can write it as minus half gmm by r. What does this mean? That means it does not have enough kinetic energy. Remember, half gmm by r. Right? So it does not have enough kinetic energy for the satellite to move away or get out of the gravitational fields of Earth. It does not have enough energy. In the case that its kinetic energy was exactly gmm by r, it could have escaped, because in that case, positive gmm r plus negative gmm by r would give you E total of 0. In that case, it would have escaped from Earth's gravity, because the net energy on it, its net energy would have been 0. That means it is under no one's influence. It is under no one's influence, right? Fair enough. So now, if I plot the energy on the y-axis and I plot the distance on the x-axis for the kinetic energy, notice it is positive. It is on the positive axis and it decreases with increasing distance, because notice the gravitational field strength would decrease. Since the satellite is in orbit, its centripetal force is provided by the Earth's gravity, right? Therefore, in the case that it oscillates, I keep saying oscillation. So in the case that it is farther away, if this was its initial orbiting circle, if it went farther away, that means the field strength at that position is less. Therefore, its kinetic energy would be less as well. Its kinetic energy would be less as well, because its speed would decrease. It would oscillate as it would orbit at a slower speed, right? Which is why its kinetic energy would decrease. Therefore, with increasing r, k decreases. Now, in case of notice its potential energy is actually supposed to be a bit over here, around about here. Yeah. So it has double amount of the kinetic energy, right? If the object, the satellite, has exactly half gmm by r, it will have negative gmm by r. So double the amount of kinetic energy, but it is negative, right? Why negative? We have discussed it previously, right? So it is unable to escape, at the end of the day, Earth's gravity or Earth's gravitational fields. However, in the case that we had a gravitational potential energy of minus half gmm by r, what we would have is a straight line. Because notice, this yellow curve would cancel out this pink curve. And in that case, the net energy on the satellite would be 0. However, since we have this red curve, which denotes minus gmm by r, therefore a more negative gravitational potential energy, that means it is unable to escape Earth's gravitational field, right? Now, how do we make the satellite escape Earth's gravity? In that case, as mentioned, the Ke needs to be equal to gravitational potential energy. Therefore, the change in gravitational potential energy, that is, if this is the object, this is Earth, this is the satellite, and this is infinity. For the object to go from this position to infinity, its change in gravitational potential energy needs to be equal to its change in kinetic energy. Meaning, it needs to have enough kinetic energy, half mv squared, such that it provides the energy that it can work against the gravitational fields, that is attractive. It will work against those fields, against all odds, and it will be free. Therefore, that change in gravitational potential energy that the object goes through in going from near the Earth's surface to infinity, it needs to be equal to its kinetic energy. Therefore, your change in kinetic energy is half mv squared, and your change in gravitational potential energy is going to be 0, because at infinity it is 0, minus gmm by r, because near the Earth's surface it is minus gmm by r. So at the end of the day, you get half mv squared is equals to gmm by r. So ultimately, to find the escape velocity of the satellite, if you make v the subject, it turns out to be v squared is 2gm by r. So v is root 2gm by r. This v is your escape velocity. If the satellite has this velocity, it will escape Earth's gravity. If the satellite has this velocity, it will escape Earth's gravity. Okay, so in our case, what happens is the orbital speed of the satellite is actually lower than this v, or this escape velocity, which is why the satellite never gets to escape Earth's gravity. This entire video has such an interesting plot line. I mean, there's a satellite wanting to leave Earth's gravity, and it is unable to, cross all odds and be able to escape all this negative energy. Anyways, going back to the topic. So we know the velocity, the escape velocity that the satellite needs to be able to be free from Earth's gravity or Earth's gravitational fields. But we know it will never be able to achieve that. However, we can find out the kinetic energy it needs because we know the velocity it needs, right? So we know the formula for Ke, that is half mv squared. Velocity is root over 2gm by r. So if we plug that in, Ke turns out to be gmm by r. So as discussed over here towards the beginning. Right, towards the beginning over here. If the Ke was exactly the same as the gravitational potential energy, it would be able to escape, right? Therefore, if your Ke is gmm by r, that is exactly equal to the gravitational potential energy, the object can finally escape, right? So that is it for astrodynamics. That is all that you need to know about for gravitational fields. And that will be it for this series. I'll try to solve a few question papers and see you in the next video.
I have just added a very different and sort of new section to the gravitational fields course or chapter, whatever you want to say. The reason I've added this little bit, I don't know where you'll be watching this video, probably a separate video or a part of our full course. But the main point or reason I'm adding this is to mainly consolidate the entire understanding of gravitational field. If you're reviewing your concepts and watching this video, then you already know many things from other chapters. And if you have just studied gravitational fields, then this will help you understand things from a bigger perspective. So that is why I say this is further understanding of whatever I'm going to go through, or gravitation fields, I mean. So let's get started. Well, till now we have mostly worked with a single mass or two masses, and we have seen how the gravitational field strength changes. So if I have M1 over here, I bring another mass M2, and we find out, calculate using the GPE formula and the force formula, how the force changes as I move M2 towards M1 and away from M1. So the force changes as the separation between these two masses change, right? And do we also know this other fact that, let's say, these masses are a x distance away from each other. Let's call that distance 40 meters, right? If the GV of M1 is minus 20 joules, what is the GPU of M2? Also minus 20 joules. I believe you guys already know the formula, GMM by R, minus GMM by R for GPE. And if you put M1 and M2 over here, let's say I'm finding the GPE for M1. So gravitational constant times the mass M1 times mass M2 divided by separation between two masses. And then for GPE of M2, it's the same thing. You write M2 times M1 divided by separation between these two masses, and that's the GPE for M2. So what is the value that you get at the end of the day for both cases? Same, right? So if it's minus 20 for this, it's minus 20 for the other one as well. Now, this is possible mainly when you are isolated in the universe. There's no other mass around you. You get that? What happens when other masses are there? Basically, the gravitational potential energies between multiple objects are added. So if there's a mass over here, M3, the GPE between this is added with GPE between this if I am finding the GPE for M1. So the GPE of M1 will be the summation of GPE between M2 and M3 and M1 plus M1 and M2. There's more to it, of course, but that's not a part of our syllabus. That's not something we need to understand. What do I want to show you guys over here is, let's say you have two masses. I want to talk about two separate masses, and then I want to introduce you guys a third mass and have a conversation there. So if you have two masses over here, let's draw the gravitational field lines. And how would you draw the gravitational field lines is my question. Typically, when you are taught in what usually teachers will be teaching you, and rightfully so, if you have a mass, the gravitational field line looks something like this, inwards, right? I've taught this to you guys as well. Inwards, right? Radially inwards, radially inwards. But what happens if there is another mass, M2? Here's the case. Let's say there's mass M1, smaller mass, and a larger mass M2. Do you see the curved nature of the field lines? Keep this in mind. Why is this happening? What is field line in general? See, field lines in general are they denote how, or in what way a force is felt by a third object. If I place a mass over here, it will straight up be attracted by m1. If I place a mass over here, it gets straight up attracted by m2. So it in nature shows the path of force, line of force acting on a mass, right? So field lines basically show you how a force is felt by a third object or a second object. When you're talking with respect to just mass m1 and I place a mass m2, then I know it will feel a force radially inwards towards m1, right? That's the concept of field line. Now, what happens to having two masses, one small, one big, and I place a third mass m3 over here? It will no longer have a straight up radially inward line of force, or it won't follow a straight path, my friend. The path is a bit different now, because now there are multiple field lines and in different directions, okay, which overlap each other. See, both m1 and m2 are attractive masses, have attractive forces. You have yet not treaded into electric fields where there are, repulsive forces. Then it's a very interesting thing there as well. Attractive forces work over here. So field lines overlap, my friend. And if that happens, field lines, think of it as a way that, I've written it over here as well. We consider the vector addition of these field lines, right? And we end up, let's say, if there's a field line for m1 over here towards the center of m1, and there's field line for m2 towards the center of m2, they cancel each other out. Okay? They cancel each other out. Do you get the point? However, what you will notice, this is not an exhaustive diagram. There are more field lines, of course. But my point is, do you notice that these field lines are more inwards? So they are taking more of this path, while this m1 field line is more away, more away, more away, while this field line for m2 is more inward, more inward. Now that is done intentionally to tell you guys something, that mass affects the power or the nature of these field lines. m2 being a higher mass has a higher strength near this area. See, if m2 and m1 were similar masses or the same exact mass, what you would have is, let's say, m1 over here, and the shape of the field lines on either sides would be the exact same. The exact same. However, that is not the case, my friend. Okay? See, there are other field lines over here as well, of course. But I've just drawn a few field lines. I can't draw an infinite number of field lines. I've drawn something just to give you a picture. So m2 being something of a higher mass has greater strength or pulling force. Okay? Now, of course, for one thing, I don't want to mess up your understanding of how field lines or gravitational fields works. m1, what is the force felt by m1? Let's say x towards m2. I'm talking about m1 with respect to the center of m1. Please don't get confused. And if I'm talking about m2 with respect to its center, what is the force felt by m2 due to m1? The same force, x Newton. Why? F is equals to gmm by r square. So what shenanigan am I talking about when I'm talking about these field lines? What I'm talking about is bringing a third mass m3, right? And what force would this field being around these two masses? That is what I'm talking about. So please don't get confused. Okay? So if I bring a third mass, what is the field? What is the force felt by that third mass? And I'll get into that. I'll show you the graph, I'll show you the maths, and it's very interesting. And it will sort of give you a good picture of how to imagine the maths, the force maths behind multiple objects, multiple masses, not just two masses. So, see, at the end of the day, the field lines denote the line of force or how strong the force is. The force, if I have a third mass coming in, right, it will feel a larger amount of force towards M2 if it's positioned somewhere over here. And if it's positioned somewhere over here, it feels a larger force towards M1. We can quantify all of this, of course. We can quantify all of this, but we'll do that downstairs below. But at the end of the day, the field lines would look something like this. A few people, not a lot, a few people have asked me, if you have like forces over here, how do the field lines look like? Why is there a gap here? The gap is because the field lines can't see each other out, right? The field lines can't see each other out, right? So that is the main idea over here that I want to show you guys. I want to show you guys the field lines, how if two masses attractive forces apply over here, how would the field lines look like? I hope you get the idea. If you have any question, do let me know. Great. Now I've talked about this. Yep, I just told you guys that the field lines bending inward for the mass M2 is simply stronger. So you see, these field lines will be curving more over here. Okay, because strength for M2 is great. And there's a point over here. There's a point over here somewhere where M3 will feel zero force. Can you tell me why? Because M3 will feel, if you calculate the force between M3 and M1, so now you're calculating between M1 and M3. So M3, let's say, is 1 kg. So if I'm using the same F is equals to GMM by R square, right? And you try and find the force between M1 and M3, you would require a smaller separation between M1 and M3 to match the force of M1 and M2. Why? So a lower separation means higher force. So due to the M1 being a smaller mass, M3 has to be positioned closer to M1 such that that force between M1 and M3 equals the force between M3 and M2. Do you get that? So somewhere over here, if I had to draw this diagram more correctly, actually, I'll do that for you guys right now. It would have to, where's the pink? It would basically be, there would be a gap over here, somewhere over here, and there would be more field lines for M2. Do you get the point? Are we getting the point? So there will be more field lines towards M2 over there, and there would be a small gap over here. And that is where, due to vector addition of the field lines, you have net zero force on the third mass. Okay? So this sort of gives you a better picture. Okay? And number of field lines, again, what does that denote? Strength of the force or gravitational field strength. Higher number of field lines denote greater field strength. Great. So that's what I wanted to put across. I guess I wasted too much time talking about it. Sorry, my bad. But fair. What, am I missing something? Right. Again, just to clarify, if over here there's zero field line over here and M3 doesn't feel a force over here, if I position M3 right at that position, M3 right over here, M3 doesn't feel a force because equal force from M1 in this direction, equal from force from M2 in this direction. But does that mean M1 and M2 doesn't feel a force? No, M1 and M2 always feels a force. What I'm talking about is bringing in another mass, putting it over there, and does that feel a force? No, because equal forces from both sides. But obviously, M1 and M2 are attracted. They're always going to be attracted, my friend. If I'm talking about these two separate masses in the universe, in isolation, These are always feeling a force towards each other. Okay? Do you get that? Doesn't matter if there's a field line gap over here. They do feel a force, regardless how you think of it. Okay? And this is literally the line of, the line in which they will move towards each other if left freely. Great. 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 Now, we are taking the same example as above. We want to do a bit of maths, right? So, what can we do? I mean, I've just explained this above. If M1 has a certain GPE, like both of these are isolated in the universe in space-time, M1 has GPE, let's say, minus 20 joules, and M2 has GPE minus 20 joules. This concept should be clear to you guys. Why? Because GMM by R in both cases apply the same way. So the same numbers go into the formulas. And that is why the GPE for these two masses will be the same. Do you get that? Why is that the case? Let me conceptually try to put this across one last time very fast. If I bring M1, this same mass, M1 from infinity to this defined point 40 meters away from M2, I lose a certain amount of energy. Okay? Okay? And what is that certain amount of energy decided by? How much force acted on me throughout the process. GP is work done. Force times distance. Do you remember the derivation we did? Area under the curve. Do you remember that? Good. Remember that. Recall that. So if I was really far away, force was less. Let's say 21. Then I came a bit closer. M1 came a bit closer. Force on me was, let's say, 30 Newton. M1 came even closer. Let's say now the force is, 40 Newton. Right? So from 21 to 30 to 40 to something over here, 50 Newton. Now M2, for M2, at exact these distances from this side, bringing M2 from infinity, let's say it faced 21 newtons somewhere, I mean same separation as M1, and then it comes towards the next same separation and it faces the same force, 30 Newton. Again, closer, 40 Newton. Over here, 50 Newton due to being 40 meters away from each other. So my point to you guys is, it's the same concept of Newton's third law. The force applied on both of them at equal distances away from each other is the same. So when you're bringing both of them close together, same force is applying at any given distance. It's 50 here, it's 20 here, 30 here, 40 here, 50 here. Both of them are feeling the same increasing force. Okay? So if that's happening, the work done on both of them is same. That is why GPE on both of them is same. Did I get that across? If you don't get it, ask me. Okay? Just simply ask me. It doesn't hurt to ask. Make a different account and ask on YouTube. In the comment section. Just ask. Ask Gemini, ask someone. Don't sit down with confusion. Good. Do we know this graph? Please? Yes? Perfect. I hope that the answer is yes. So the GPE concept is, if the two masses, mass 1 over here, M1, mass 2 at infinity, if M2 comes closer, both of their GPE, it's the same. Both of them have the same GPE. Highly negative. Closer to infinity. As you move closer, goes to infinity. As you move away, goes to what? The GPE goes to what? 0. Why does it go to 0? Because when it's closer together, they have attractive forces, right? And if I try and push it away, I'm doing work on it. And when I take it to infinity, we have decided collectively, the scientific community has decided, at infinity we will say the object will have 0 joules of energy. So we increased from a very negative value to 0. That's how the maths work. And then when you come from 0, that is from infinity, it loses that energy that we provided it to push it to infinity. You get the connection? You connect the dots? Good. Hold that thought. I've taught you guys about control lines as well, somewhere above. If I have not, no, actually I have not. I've taught this in electric fields. Anyways, control lines basically define field strength. Actually, I've taught you guys this, no? Well, if I have not, let me just quickly run over what control lines mean. So, you study this very effectively in electric fields. I've taught this. Don't worry about it. Well, control lines are basically it defines electric field strength. In this case, gravitational field strength, right? So if you have mass m1, and I draw a control line over here, okay? Next control line over here. Third control line, or concentric circles, as we say. There. What do you notice? Oops, that is not what I wanted to do. My friends, do you see that the separation between consecutive control lines increase? Good. That is what I want you to notice. The main point of doing control lines is if I have a mass, second mass, m2, the force felt over here on this concentric circle, or that is the mass's surface. Let's say the mass's surface. So on the mass's surface, it faces a force 100 newtons. Agreed? Now to have a 10 Newton drop of force, you move away and the force decreases. I hope you know that. You move this much distance, that small amount of distance, to have the force decrease to 90 newtons. Okay? Wait. Okay. So this small gap or separation, change in distance, has decreased your force to 90 newtons. Now to have the same decrease in force of 10 newtons, so to go from 90 newtons to 80 newtons, I have to travel a larger distance. Are we getting the point? Yes? So now it's 80 newtons. Now again, to have the same decrease of 10 newtons, I have to travel a larger distance. Why is this? Remember the graph. If you don't remember the graph, I don't know what you're doing. Please remember the graph. This is the graph. Seems okay? This is gmm by r square. This is surface. Gmm by r squared. Okay? F is equal to gmm by r square. This is the surface. This is the center of mass. Okay? Now, where is this? Okay. Now look. My bad. So now look. If I want, let's say, this is how much decrease in force. Let's say this is 10 newtons of decrease in force. It's 100 newtons here and 90 newtons here. Okay? To have the same decrease, let's say over here, 80 newtons. Do you see x1 to x2 to x3? To have the initial 10 Newton drop, I travel from x1 to x2, small distance. To have the same 10 Newton drop from 90 to 80, see how much more distance I had to cover. This is the changing gravitational field strength. So the field strength decreases as you move away from the mass. So that is how, drawing these control lines, that defines the, changing field strength, that the fact that the force decreases as you go away. Okay? Field strength decreases as you move away. That is the main thing. I hope you get it. Now my point is, what happens when you have two separate masses? What happens to the control lines? How do they look? I have drawn something very whack, but it puts out the same concept out there to you guys. So basically the lines combine and you have a gap somewhere over here. To be very honest with you, these lines would warp in a lot more, keeping a gap somewhere over here. And why is the gap here? I just stopped this to you guys. The force over there felt by a third mass is 0. That's why you have a gap over there. But the control lines basically mean, if I have a mass m3 here on this line, on this control line, anywhere on this control line, it feels the same force. So if it's feeling 20 newtons on this place, it feels 20 newtons here, 20 newtons here, 20 newtons there, 20 newtons here. Keep that in mind. Keep that in mind. Okay? Okay? So over here, let's say 30 newtons. Not 30, it should be less. So 15 newtons. So everywhere on the second control line, it is 15 newtons. Good? So that is the point of control lines. Now, the point of showing this is really that when you have two masses, the control lines combine together and you have a, the concentric circles, the control lines will join and you have more space for the mass to travel around in while feeling the same force. Okay? So that is what I want to put across. I've covered everything. Good. Now comes the maths, the fun part. Okay? Now, what we want to see is when you have two masses, A and B, M1 and M2, if I bring a third mass, M3, the red blob, and I move it between the spaces, how does the force vary? Okay, I want to graph it out. So the mass of the M3 is 1. What does that mean? The smart ones, or everyone is smart. Why have I chosen 1? The reason I've chosen 1 is that basically defines, if I'm trying to find the force for M3, right? The force felt by M3. Let's say, forget about M2. I'm considering how force is felt on M3 by positioning it around M1. Forget about M2 for now. Let me put the concept across first. So between M1 and M3, I'm moving M3 away and seeing how the force changes. Okay? So it's M3 times M1 divided by the separation between M1 and M3. Okay? So now, my friend, if I have M3 as 1 kg, what does this formula give you? Gravitational field strength. I have it written over here. So the reason for considering M3 as 1 is such so that I can work with the gravitational field strength of M1 and M2. So it simplifies things. So what happens? So what I ultimately want to find out is what is the force felt by 1 kg of mass when it is positioned in a space which consists of M1, mass M1, and mass M2. So I want to move around M3 between that space. Okay? So what I actually do is I sum up the gravitational field of M1 and of M2. And that net gravitational field is the force felt by a third mass. By a third 1 kg of mass. Get the concept? Okay? Beautiful. So I'm positioning M1 and M2 40 meters away, and G I'm considering as 1. So gravitational constant is 1. Why and how can I do that? How dare I? Look, g can be anything. It's a constant. Imagine x squared. Okay, so it's a quadratic curve. It's a happy face curve, as we were taught. If you add 10 in front of x squared, what happens? It's skewed, right? It gets sharper in nature. That's the main point. That's it. That's literally it. The shape is still a happy face curve. It is simply how skewed it gets. Okay, the core shape stays the same. So G doesn't do much except for changing the skewness in some way. So I'm omitting that. What I want you guys to understand is the shape of the graph. So look, you study this in gravitational field, electric fields very elaborately, but I want to apply the same thing over here. The main point of studying, A-level stuff or anything advanced is your ability to apply one knowledge in other places, right? You should be able to apply the logic. You're building logic. You're probably not going to study physics later on. Who knows? You need the logic. You need the ability to apply things in other places. So my point is, look, you have this M1. This is the surface of M1, and this is the center of M1, positioned right at 0, 0. And then you have the surface of M2 and the center of M2 positioned right at 40. Okay. So on the coordinate system, I've placed M1 on 0, 0 and M2 on 40, 0. You get that? Beautiful. Now, what have I plotted over here? What I've plotted really is the gravitational field strength of M1 and the gravitational field strength of M2. Do you see that? Yeah? Perfect. So, by the way, just to tell you guys, for M1, let's say if this is the center and again, this is the other surface because the circle goes like this, right? The circle goes like this. So, the gravitational field is highest near the surface and then decreases as you move away. Same happens on this side. Highest on this side and then decreases as you move away. Got it? So this same curved graph is also on this side. Please don't be confused. Same with M2. If it's happening over here, it's also happening on the other side. So don't get confused. I'm just looking at the space in between. Okay? Perfect. Now, can you guys tell me what is the net graph supposed to look like? So this is the main graph. Like this is one of M1 and this is the one of M2. If I had to draw the net gravitational field felt by M3, how would you draw it? Think guess. The hint is you sum up the graph. Okay? So for this graph means that, the reason it's towards this direction is because M2 has field lines coming inward from here. So towards the right, I would say. If I'm considering the space in between M1 and M2. Okay? And then M1 has field lines coming in this direction. So towards the left. Get that? So both of them field lines are opposite in direction. And what are we plotting? Force versus distance or separation. Force is what? A vector quantity. So if this graph of M1 denotes force or gravitational field strength of M1 in this direction, in the leftward direction, and for M2, this line denotes the gravitational field strength in the rightwards direction, both have different direction of force. So one is positive you can arbitrarily choose which is positive, which is negative, and the other is negative. The point of positive and negative is both are opposite to each other. So when they sum up, they subtract away from each other. So this red, so if it is 10 over here and this black point over here, right? If you had to sum it up, it would be something like 9.95 or something like that. Then you sum up over here. The value over here is around, let's say, 1. And then you subtract minus 0.2. So the ultimate force or gravitational field strength will be 0.8. Similarly, you do that for all the points on the graph, all the points from the red line to the black line, for all of the points on the x-axis, all the points on the x-axis, you sum up the y values. Consider, let's say, the black line to have negative force and the red line to have positive force. And ultimately, what would your line look like? I'll make another try. Perfect. So the orange line is the ultimate line. When you sum up both the forces, notice over here, it is connected to the x-axis. Why? I'm coming to that. That is very, very important and the very important maths part. Why is it connected to the x-axis? Can you guess? Can you guess? Because exactly at this coordinate, the force from M1 on M3 and the force by M2 on M3 is exactly equal. How do we find that out? Mathematically. I've done that for you guys. If I was, your teacher, I would be making some really weird and interesting maths for you guys. And this is one of the things I would ask you guys to solve. Anyways, so the math looks like this. Why is the force equal at the black point? This point. This point. Why is the force equal? Let's see. Let's mathematically find out. So what we want to find out is when is the gravitational field strength between when is the gravitational field strength for M1 and M2 exactly equal? Now, the reason I'm not considering the third mass, M3, is because it has 1 kg of mass, right? So when you're finding the gravitational field strength, you're automatically considering what is the force felt on 1 kg of mass, right? So it is the interaction between M1 and 1 kg of mass. That is what gravitational field strength tells you. What is the force felt by 1 kg of mass, right? And same with M2. The gravitational field strength of M2 tells you what is the force felt by 1 kg of mass due to M2. So that is why we are working with gravitational field strength. I already told you guys this. So even in the maths, what we want to really put as equal is the gravitational field strength of M1 and of M2. And we're going to find out at what coordinate is it equal. And funnily enough, it is exactly this point, 14.64. Let's find it. So what is the GFS for M1? It is GM by R square. What is R? R is basically starting from 0 to any point from 0 to 40. Okay? So that is R. And for M2, the separation would be 40 minus R. Why is that? My friend, use your brain. I mean, if you don't understand, it's fine. I'm explaining it anyways. See, if this is the center and this is 40 and this is 0 and this is where M1 is and this is where M2 is. If I have my black dot over here, what is the separation over here? R. And what is the separation from M2? 40 minus R. Got it? So as I move this X or my black dot or mass M3 really, why am I saying black dot? So as I move the mass m3 around, the separation from m1 to my mass m3 is r. And what is the separation from the mass m3 to m2? 40 minus r. So if this distance is r, the balance would be 40 minus r. So that is why, right? That is why we say 40 minus r. That is a simple reason. Okay. Now, when we do the calculation, we do everything. And at the end of the day, you get a quadratic equation. And you solve for r, you get r is equals to 14.64 and r is equals to minus 54. This is irrelevant. Negative can't happen because we know the physical constraint. So it is r is equals to 14.64. So this proves that the gravitational field strength at exactly 14.64 is 0. So that means this, in this place, if I place m3, it feels 0 amount of force. Right? Great. And that is pretty much all I want to talk about. Notice again, I talked about this, above, that the equilibrium position or the place where the force is equal is closer to the smaller mass. M1 is the smaller mass, M2 is the larger mass. So, it's oops. So, this balance point where force is equal is closer to the smaller mass. I explained this above when talking about why there is a void over here, right? So hopefully I could connect all the dots. The reason for talking about this is really to give you a picture of how to connect ideas. You shouldn't just learn formulas. You shouldn't just understand things in a sandbox. You should be able to extrapolate those ideas and apply in different dynamic situations. And I hope I could help you guys in somewhat way. I'm shooting this video after probably 1.5 years from my previous videos that I shot for gravitation fields. But yeah, thank you for watching. I made this a way too long of a video than I needed it to be, but I want to make sure whenever you're watching this, all the previous concepts are clear to you. Okay, so see you guys.